Okay. Hello, everybody. And I have a great pleasure to speak here with this talk. Thank you, Alexander Yakovlevich and Alexei Yulievich. I will speak about complex analytic quantum groups. But warning, this is not a C-style algebraic quantum group or something in this sense. This is alternative theory. And now some references.
Вот и Герхард появился, между прочим, Олег. Вот. Теперь вот что же сделать? Вот у меня вот все наши участники закрывают ваш текст. Вот как бы мне это сделать, чтобы не разъединить бы? Вот. Может, я так, может, попробовать пошевелить как-то.
А сейчас само появится, наверное. Сейчас Олег экран свой покажет, и мы будем все его видеть, я так думаю.
Понятно, хорошо.
Так, ну, экран виден?
Нет, пока нет.
Пока нет, да.
Стоп.
Вот.
Пардон.
Видны вот наши слушатели, а они закрывают ваш скрин.
Wait a minute.
Мы wait. Вот, сейчас.
Вот. Ага.
Вот так вот, хорошо. Слушатели поехали вправо, а вы теперь... Ну, у вас почему-то референс сразу. Это как? В начале? Вы к началу можете? Слон какой-то.
Что-то не то.
Пингвины.
Пингвины, понимаете ли. Ну, это я понимаю, что они тоже слушатели, но...
Не русскоязычные, наверное.
Да, именно. Это хорошо, что вы по-английски. Да. Именно для них. Так, опять референсы.
Я вообще экраны не вижу. Что-то я не то сделал.
Нет, references тут так вот написано. References. Так, а это что?
No.
Ну вот ваши references. Но это, наверное, заканчивается ваш текст.
Да, экран виден на последней странице.
Да. А вы давайте первую. План.
This is the first page.
Yes,
okay. Complex analytic quantum groups. And this is the second page. Okay.
Again, the last page.
Yes. So these four papers. First about main theme of this talk, holomorphically finitely generated Hopf algebras. And the second and the third about some examples. And the fourth about holomorphic reflexivity conditions.
That's what we
plan. I begin with examples.
Yeah.
The first example is a deformation of the universal enveloping algebra of the non-abelian two-dimensional Lie algebra. And next, complex analytic forms of Drinfeld-Jimbo algebras. And then some general theory, commutative case, cocommutative case, and holomorphic reflexivity. And this example of a quantum group, it is not very popular, but rather interesting. We take the universal enveloping algebra of two-dimensional non-abelian complex Lie algebra and deform the universal enveloping algebra of this algebra AF1. And it has two generators, X and Y, and a relation. The commutator of X and Y is Y. And next we deform multiplication. Here, H bar is the hint of Planck constant. We take the commutator, and this commutator is equal to the fraction. Here we take hyperbolic sine over hyperbolic sine. The example was considered by Aizawa and Sato, and some similar relations in Madrid. And now also I show the formulas for co-multiplication and the antipode delta and S. And note that delta and S for Y is undeformed, but for X are deformed. And here we have a common problem. We want to apply hyperbolic sign or other function to elements of some algebra. But the hyperbolic sign is not a polynomials. There is a traditional common solution when h bar is treated as a formal variable, and we have a deformed algebra over the algebra of formal series, C H in double brackets, so-called H-adic form. But I propose another solution. We know that the hyperbolic sign is an entire function. And when we take an entire function of an element, when the algebra is a Banach algebra, and in a more general situation, if the algebra is an Arens-Michael algebra, that is a projective limit of Banach algebras. And then we can treat H as a fixed number in C with that is not a zero of the hyperbolic sign, because we want to divide. And now we consider the universal Arens-Michael algebra generated by X and Y, subject to the relation as before. But the universal algebra means that we take the algebra of three entire functions and we take the quotient over the closed two-sided ideal generated by this relation. And I recall what is the algebra of three entire functions. This is we take series of inverts in some number of generators. In our case, for example, 2 generators, with restrictions which are very close to those that we have for entire functions. And in this sense, we have the algebra, which I denote by Untitled. This algebra is homomorphically finitely generated for HFG in the sense of Perkovsky. And the first theorem is about the structure of this algebra as a locally convex space. So Untitled is topologically isomorphic to the projective tensor product of the direct product of an infinite number of factors. And so C of Yn is the algebra of formal power series, and where Yn corresponds to a zero of hyperbolic sign. And O of C are entire functions, and the product tensor product is projective, complete tensor product of locally convex spaces. And but we want to consider this algebra as a Hopf algebra. But of course, Hopf algebra is not in the standard sense as but as a topological Hopf algebra. here the old tradition to read topological Hopf algebra, but to write here the sign of projective tensor product. And when we say a topological Hopf algebra, we mean a Hopf algebra in the category of complete locally convex spaces with the projective tensor product. And the projective tensor product is compatible with holomorphic functions. But in fact, since the spaces of holomorphic functions with nuclear all tensor products are compatible. Nevertheless, the tensor product of OU and OV is just the O on U times V. And the theorem says that our Untitled is an infinite dimensional topological Hopf algebra with respect to delta, epsilon, and S as determined by the formulas above. It seems I have not defined epsilon, but doesn't matter. The standard formula for epsilon co-unit. And so we have a topological Hopf algebra, and which is also is HFG algebra. And so we define this following object, Hopf HFG algebra, as topological Hopf algebra, that is HFG. Yeah, this is the first example of this type. And now, next series of examples, Drinfeld-Jimbo algebras. Drinfeld-Jimbo algebras are very popular, and there are deformations of U of G, where G is a semi-simple Lie algebra. Of course, all algebras here over C. For example, if we take SL2, it has 3 generators, E, F, H, and 3 relations. First, to relate 2 generators, and the last relate all 3 generators. And then U of SL2 is a universal associative algebra subject to this relation. And of course, there is H-adic variant where H bar is a letter and not a number. Only the third relation is deformed in this way, again with hyperbolic sign. And again, H bar is an algebra over full series. And if we want to make H a number, there is 2 ways. First, traditional way to make the exponential form. So we denote the exponential of H by Q and the exponential of H bar big H by K, and then all 3 relations become in this form, take this form. But there is another way, as in the previous example. We suppose that H is a number, and we take the universal Arens-Michael generated by 3 generators with the same relation as for H-adic form. And then again, we can prove that this universal algebra is infinite dimensional Hopf HFG algebra, and with respect to standard operations, co-multiplication, co-unit, antipode, I write here this formulas only to show that everywhere we have entire functions. Oh, in fact, only one entire function, the exponential. So we have no problem to define this operation, because in Arens-Michael algebras, every entire function of an element is well defined. And but now I return to the first version, traditional version, because my initial motivation is to find the Arens-Michael envelope of UQ of SL2. And I recall that as UQ have generators E, F, and K, and the parameter is Q, not H. Oh, 2 words about Arens-Michael envelope. They arise when we approximate an algebra by Banach algebras. For example, if we take an associative algebra OVC, then the Arens-Michael envelope is the completion with respect to all possible submultiplicative prenodes. And we denote it by H hat and consider it with the homomorphism from A to H hat, just the completion homomorphism. Or equivalently, H hat is the protective limit of all possible Banach algebra completions. And it has the universal property that every homomorphism from A to a Banach algebra factors on iota. And of course, the structure of A hat is closely related to representations of A on Banach spaces. And the envelope functor can be considered as a functor from algebraic geometry to non-commutative algebraic geometry to non-commutative complex analytic geometry, because it works well in the commutative case. This is a result of Perkowski. And now very important fact that if H is a Hopf algebra in the usual sense, then H hat is the Hopf algebra, topological Hopf algebra. That's also the result of Perkowski. And if we begin with an affine Hopf algebra, no, this is standard terminology in Hopf algebra theory. Affine means finitely generated as an associative algebra. So in this case, H hat is HFG Hopf algebra. So our main and so we have that H hat Q is Hopf HFG algebra because it is the Arens-Michael envelope, and U-tiled is HFG by construction. And then I I'm interested in the structure of underlying locally convex spaces. So why? Because the functor of the envelope functor sometimes can maps the algebra into trivial algebra or into a very small algebra. For example, the Weyl algebra, the Arens-Michael envelope of the Weyl algebra is trivial. So if we want to study our algebras, we need to understand that they are sufficiently big. The first case is when the modulus of Q is 1. So in quantum group theory, for example, for Drinfeld-Jimbo algebras, there are two different cases when the parameter is a root of unity or not a root of unity. And here we have three cases when the parameter is not or is a root of unity, is not a root of unity but has modulus 1, or when it has modulus not equal to 1. In this first case, when in the case when the modulus is 1, Pechenko found some power series descriptions of UQ hat using analytical extensions or extensions. Sorry. And if also Q is not a root of unity, then there exists topologically irreducible representation of UQ on a Banach space, even on a Hilbert space. But this argument does not work when Q is not a root of unity. And it is well known in the quantum group theory that if Q is a root of unity, then all irreducible representations of UQ is finite dimensional. But there are finite dimensional representations that are not completely reducible, nevertheless. And when we look at the case when the modulus is not 1, then the structure of UQ hat is similar to that in the classical undeformed case. And Joseph Taylor did it in 1972. He proved that if G is a semi-simple Lie algebra, then the Arens-Michael envelope of usual undeformed universal enveloping algebra is topologically isomorphic to the direct product of a countable family of full matrix algebras. And here, this countable family is just the family of all classes of finite dimensional irreducible representation. The idea of Taylor's proof is analytical. We pass from G to a semi-simple Lie group, take a compact form, real form, compact real form, and next use the representation theory of compact groups. But we have no similar technical tool for deformed. For the deformed algebra, UQ maybe at least, but this is the situation now. And there is an alternative proof. To use idea is to use an algebraic argument to show that E and F are unimportant when it's when there are elements of Banach algebra. And now we have a result that is similar to Taylor's result in the case when the modulus is not 1. The range of any homomorphism from UQ to the Banach algebra is finite dimension. And the anisymmetric envelope you had is topologically isomorphic to the direct product of a countable family of full matrix algebras. Here, B easily follows from A, since every finite dimensional representation is completely reducible. And here also every factor in this direct product corresponds to a finite dimensional reducible representation. So now I show the sketch of the proof. It has two parts, analytic and algebraic. Analytic is very simple. We need only one lemma. We have two elements in a Banach algebra, A and C, and A is invertible. And A, CA minus 1 is equal to gamma C when the modulus of gamma is not 1 and not 0. And then C is nilpotent. The proof is short. We assume that Cn is not 0 for every n, and this simple calculation shows that then the modulus of gamma is at most 1. And then we replace C by D, which is A minus 1. And we have similarly that the modulus of gamma minus 1 is at most 1. And we have a contradiction. And so if we have three elements in the Banach algebra, E, F, K, with quantum SL2 relations, and first two relations, it is of the above form. And if we assume that Q the modulus is not 1, so if E and F are nilpotent, and this is the only analytic idea here. The algebraic part is longer, but the idea is simple, and we does not need to assume that B is the Banach algebra. We need that Q is not the root of unity, and E and F are nilpotent. And then we can find for every M a non-trivial Laurent polynomial in K that belongs to the ideal generated by EM. And then calculations, and we have the closed subalgebra generated by EFG is finite dimension. And so the range of every homomorphism to a Banach algebra is finite dimension. And now I return to the second version, Untitled, and know that we have a very simple relationship between these two versions and the homomorphism from UQ to Untitled, E to E, F to F, but K to the exponential of HH. And so some questions, but not all questions, but some questions on Untitled can be reduced to the well-known representation theory of UQ. And the following result is, we assume that EH is not the root of unity, and then the range of any continuous homomorphism from Untitled to the Banach algebra is finite dimension. And every continuous finite dimensional representation of Untitled is completely reducible. And finally, Untitled is topologically isomorphic to the direct product of countable family of full matrix algebras. And as to irreducible representations, every such a representation corresponds to two such representation of UQ, but every such representation of U, the undeformed algebra, corresponds to an infinite series of finite dimensional representations of U-tile. So the theory, representation theory is wider in this case. Excuse me.
Что там? О,
Sorry. I have so some words about the general case when G is not only SL2 but also arbitrary, semi-simple, complex Lie algebra. The Drinfeld-Jimbo algebra in this case is generated by a tuple of triples, and inside of each triple we have SL2 quantum relation, and also we have some additional relations between triples. And the main result on UQ holds on arbitrary G in the case when the modulus is not 1. And the range of any homomorphism with Banach algebra is finite dimensional, and the Arens-Michael envelope is a product of full matrix algebras. As to H-tiled, so I have no proof because I will explain later, okay, in the end of my talk. So what these two tables show what we know about these two versions of different Jimbo algebras. The first variant, classical traditional variant. So we have three cases. The modulus is not 1, the modulus 1, but Q is not a root of unity, and when the third, when Q is a root of unity. And what to know about representations? In the first case, all representations are finite dimensional and completely reducible. In the second case, I don't know some restrictions. And in the third case, we know that there are infinite dimensional representations. Of course, in Banach space of representation here. And also about irreducible representations. In the third case, all representations are finite dimensional, but in the second case, there are topologically irreducible infinite dimensional representations. And in the third case, all irreducible representations are finite dimensional and have bounding degree. And in the second table, situation with U-tile is simpler because the first and the second cases are merged in one. And when EH is not a root of unity, then we have situation as in the first case, in the first table. And third lines in both tables are the same. So I finished with examples, and now some general ideas. So I say some words about geometry. So I recall some ideas. As we have some relation between spaces and commutative algebras. In topology, when we assume, if we assume that a space is locally compact, then it corresponds to a commutative sister algebra. This is the theorem of defined neighbor. When the space is affine variety, then it corresponds to commutative finitely generated algebra. This is a standard fact in algebraic geometry. And for us, the complex analytic case is more interesting. We take complex analytic space, in fact, Stein space and finite dimensional Stein space. Then Forster proved that the category of finite dimensional Stein spaces is anti-equivalent to the category of Stein algebras. But a Stein algebra is just the algebra of holomorphic functions on some Stein space. And Perkowski noted that, in fact, every Stein algebra is just a commutative HFG algebra, holomorphically finitely generated. And so when we consider the general non-commutative case, we can speak about sister algebras in locally complex case, finitely generated algebras in algebraic case, and about HFG algebras in complex analytic case, but without the restrictions on commutativity. But our case is the group case and the case of Hopf algebras. What we have for groups and Hopf algebras. If group is locally compact, then we have commutative sister algebraic Hopf algebra. When I say sister algebraic, means in the sense of Voronovich or in the sense of Usterman-Weiss. In fact, this algebra can be multiplier of algebra and so on. When group is affine algebraic, then we have a commutative finitely generated Hopf algebra. Because Cartier's theorem asserts that every affine algebraic group scheme over field characteristic 0 is non-singular. From this, we can easily derive the fact that every commutative finitely generated Hopf algebra corresponds to an algebraic group. And what in the situation with complex groups? So I suggest to use HFG Hopf algebras as the alternative for Stein groups, for example. And maybe, at least it is a first approximation. Maybe the class must be wide or must be narrow, but as the first approximation, I think it's okay. And to justify this, I consider first commutative Hopf HFG algebras. We take complexly group G and the following factor, which maps every Lie group to the commutative Hopf HFG algebra of all holomorphic functions on G. And this function Hopf algebra has standard operations for multiplication delta, for unit epsilon, and the antipode S. And here the result is that, in fact, we have an anti-equivalence of categories. So the restriction of this functor to Stein groups is an anti-equivalence of categories of Stein groups and commutative Hopf HFG algebras. And the argument is similar to the proof of Cartier's theorem. And so we can really treat general Hopf HFG algebra as a non-commutative analog of the function algebra on a complex Lie group, or at least on a Stein group. And so we can call the objects of dual category as complex analytic quantum groups, or for example, as quantum complex Lie groups. The second standard case in the Hopf algebra theory, the case of cocommutative Hopf algebras, when we have no restriction on the multiplication, but we assume that the co-multiplication is cocommutative. And here we also take a Lie group and consider the algebra of analytic functionals. It can be defined as the strong dual space of the space of holomorphic functions on G. Strong dual in the sense of functional analysis. Continuous linear functionals with the topology of uniform convergence on bounded sets. And the outer structure on A of G is the same as on the group algebra. Here G without topology. And these are formulas for delta, epsilon, S. And this Hopf algebra structure is extended to the topological Hopf algebra structure on A of G. And next we consider the Arenspark envelope of A of G. And the result is that if G is compactly generated, then A hat of G is the Hopf HFG algebra. H hat or A hat of G is the envelope. And the proof is heavily based on the theory of locally convex spaces. So we have another series of examples of Hopf HFG algebras. And I also note that, in fact, the class of cocommutative Hopf HFG algebras is wider. If we take the free Lie algebra in A generators, then H hat of Fn, which is in fact is the algebra of free entire functions. And this algebra is a Hopf HFG algebra, but there is no Lie group such that it's the Arenspark envelope of H A of G is coincide with H hat of Fn. And no, by tradition, we look at the structure of a locally convex space. And when G is connected and linear, that is, there exists a faithful holomorphic finite dimensional representation, then G can be decomposed into a composition series such that G over B is linearly reductive, B over E and E are simply connected and nilpotent. Linearly reductive means that not only has reductive Lie algebra, but also is the complexification of a compact Lie group. And then as a locally convex space, H hat, A hat, sorry, A hat of G can be decomposed in 3 factors. And here, the first and the second are also of the form H A hat, and the third is the space of formal power series with respect to PBV basis. And we also can describe the structure of first 2 factors, because A hat of G over B is the product of full matrix algebras also. And B over E is simply connected and nilpotent. And in this case, A hat is the power series space, but some restrictions on growth. And the last topic today, if you have some patience, okay, about holomorphic reflexivity. Was Akbarov who introduced holomorphic reflexivity. And look on this diagram for complex Lie group. We begin in top left angle O of G, holomorphic functions. And then we apply strong dual, and we get A of G, analytic function. Then we apply envelope, we have A hat, and the structure was described in connected case in the previous slide. And then we apply again strong dual functor, and we have so-called functions of exponential type, but no definition to there. And then again apply envelope functor. And here, all spaces are Hopf topological algebras, and also O or G is always a HFG, and A hat is HFG. Not totally connected, so also. And we say that O of G is holomorphically reflexive if this diagram commutes. And the result is that if G is a complex Lie group with finitely many connected components, and we denote the component of unity by G0, then O of G is holomorphically reflexive if G0 is linear. Some words about the history of this theory. Akbarov introduced this scheme and claimed, but optimistically, that reflexivity holds for G with countably many components. And with G0 algebraic, that also conjectured that it holds when G0 is linear. But there was a gap in the proof, but this gap can be filled. But also there are counterexamples for the countable case. But in the case of finitely many connected components, everything is okay. But nevertheless, there is a conjecture that the restriction in components can be removed by using so-called generalized linearity when we assume that the group has possibly infinite dimensional spaceful holomorphic representation. And so now summary. This is the table groups-wise Hopf algebras again, but now I filled it. And in the third line, we see Stein groups, commutative HFG Hopf algebras, and in general, non-commutative HFG Hopf algebras. And what we have non-trivial examples. H-tiled of F1, the deformation of in the case of two-dimensional solvable Lie algebra, U-tiled of G, the deformation, the Drinfeld-Jimbo algebra, or semi-simple Lie algebras. And another variant H hat Q. Oh, and any case left is better, and H is a number and not a letter. Also, the commutative case is understood, and there are some results in cocommutative case. So we have a theory which is at the beginning. So I see here many opportunities for research in the future. And a short list of problems and questions. Maybe they're stupid, but I think the first is not stupid. How does all this relate to C-star algebraic quantum groups? Of course, I hope that such a relationship must exist. Also, in this case, the structure of U-tiled H when G is not SL2. The problem is that when I proved the theorem, I use some algebraic results and modify some argument. So, but for SL2, not very complex, but in general case, rather complex arguments, so I don't know how to do it. Also, the case of UQ for SL2, when the modulus is not 1 and Q is not a root of unity, I can prove that there exists topologically irreducible monospace representation. But what about simply irreducible representation? I don't know. Also, we have homomorphism from UQ of G to U hat, and from UQ of G to U-tiled. And the question is, are they always injective? We know that iota is injective when the modulus is 1. It follows from Pechenka result. And also, it seems we need to find a structure for general, not only associated with the Lie group, or commutative Hopf HFG algebra. And the last question is, are UQ hat and U-tiled are holomorphically reflexive or not? This is the end. Many thanks for your attention. Any questions?
Yes. Which questions, gentlemen, ladies and gentlemen? Ask our speaker. Well, I have an impression, Oleg, that you are right to write a survey article, because you have so many results now. Maybe you already systematized them, and I think that people would be very interested if, with overview, with this, with that. Yes.
Well, maybe, but I think it's too early for a survey.
Oh, no, maybe. And who is Pechenka?
Pechenka, this is a former student of Alexei.
Ah.
But I think he left mathematics.
I don't know exactly. He moved to the University of Pennsylvania about 5 years ago. and began to work in algebraic geometry. But well, I don't know if he actually left mathematics. Maybe he's still there.
Traditional way of Grothendieck, from functional analysis to algebraic geometry.
Yeah.
Well, no, there are cases when somebody left for several years, then returned and did excellent things. For example, Matt Dawes, you know, from Leeds.
Mhm.
That's an example. Now he produces very interesting things. Yeah. One silly question. You quoted, you have quoted Taylor.
Yes.
And I vaguely remember that there was, as you say, optimistic things, and in his proof there were gaps and even counterexamples.
No, not gaps. There is a gap in Akbarov's paper.
No, Akbarov, it's another thing. I mean, Taylor, something again. No, well, maybe I'm wrong. But we even had a discussion, but it was so long ago that, okay, I shall try
No, I
to revive in my memory.
I checked the proof. It's rather easy.
Yeah,
But in any case, when we have an
even in commutative,
alternative proof, so I think the result is result
even
false.
the commutative case, something was suspicious. No, well, it's maybe I'm wrong. So other questions, please.
I have a question about representations of U, Q of G, where Q is the absolute value of Q is 1, but Q is not a root of unity. So you said that there is an infinite dimensional irreducible representation on a Hilbert space. And the question is, can we find a faithful topologically irreducible representation of U, Q of G?
No, maybe. So I haven't checked, but maybe this representation is faithful. It's possible that this representation is faithful, or maybe some direct sum of such representation. In fact, a series with parameter of such representation.
So it can happen that the representation that you have constructed is already faithful. Yeah,
Maybe it is possible.
Okay.
I have a question too.
Yes, please.
So you have the holomorphic reflexivity, which is a kind of duality, in the commutative case of complex Lie groups, okay, which are in fact linear groups. And in the non-commutative case, in your deformations, is there any duality?
Commutative case, you mean commutative Hopf algebra, yes? In this sense.
Non-commutative. So in the beginning of your talk, Drinfeld-Jimbo, you spoke of these Arens-Michael envelopes, which are Hopf algebras. And well, in algebraic approach, they are in duality with the algebras of polynomials on the Lie, deformed Lie group. Okay, is there anything like this in your system?
Sorry, I don't understand. And another time, please. Maybe I show the page.
You return to the slide where it is holomorphic reflexivity. Okay.
Let's
This slide.
No, with a diagram just before, maybe.
Oh.
Yes. So what happens? You put instead of O of G, if you put this deformation algebra UH of small g.
So this is the question. This the last question in my list. But I don't know. So I think that if we need 2 steps, the dual algebra and second dual algebra. I think in this case the first step can be simple, but the second step I don't know. But so when I prove this theorem, I need the structure theory for this algebras. And when problem is if we don't know the structure as a locally convex space, then I don't know how to prove reflexivity. Maybe there are no, other ways to do this, but at this fact. So this,
Get a description of these algebras as locally convex spaces as a product of matrix algebras.
yes, about this.
I don't know anymore where was it, but no, I think it was before, I believe, because it was not for a group. Ah, you mean no? What I mean was not for a group, but for the deformed-Lie algebra. For UH of small g.
For UH, you tiled and you had most cases we know that they are just products of finite dimensional algebras. So we know the structure.
Yes. So it's
But
not enough.
the problem is that we don't know the structure for dual algebras. When we take in this diagram, if here we take U tiled and then we apply strong dual functor and then Arens-Michael envelope, and I don't know what this place is empty. I don't know what is it.
Okay.
Yeah. Okay. So no questions, or there are still. Okay. No, so you see, the discussion was, which is very good. So let us thank our speaker for a very interesting, indeed, very interesting talk. Yes, next time we have Yaroslav Anatolievich Kopylov. No, about what he will speak, he will send us title and abstract. I think it must be, yes, please. No, about future talks, no, when it will be time, we shall speak about this. And next will be Yaroslav. Okay, so thanks to all people who were present, and how they say, хорошего дня, хорошего вечера. Now there is a strange calca.
Have a nice night. Yes.
Yes, indeed. Sleep well, dear comrades. Okay, bye.